Okay, let's continue. This is going to be part 32 for stoichiometry. Alright, 32. Continue from the previous example, and we did not finish. Alright, so from the given quantity of 10 grams of each reactant, and then divide their gram formula weight, we find number of moles. Why we do that? Because we need a number of moles to put into the mole ratio to compare which one is exactly enough or is more than enough, right, to the other number of the other reactants. So here 10 gram divided by 78 gram per mole for sodium sulfide give you 0.128 moles of the Na2S. Now the 10 gram for lead nitrate, the gram formula weight is 331 gram per mole. Lead is heavy, right? So let's find out. And what is that? Count for how many? So 10 divided by 331, that gives you 0.0302. So basically it is only 0.0302 mole. Right? Now, if that's the case, now according to the mole ratio from the balanced chemical reaction equation, right, it's 1-to-1 ratio between the two reactants. Now here, this is 0.12, this is 0.03. Seeing this is very small, so the concept is these two supposed to be 1-to-1. So if we think this is this first reactant, the sodium sulfide, is going to be completely consumed, then we need exactly 0.128 mole of lead nitrate. Correct? 1-to-1. But we don't see 0.128. We see 0.03. Much smaller, 4 times smaller, right? 4 times smaller the amount. So it seems to be, if we react these two reactants with this kind of quantities, and this one, the second one, the lead nitrate, will be first completely gone or consumed. And this one will have exactly 0.0302 mole out of 0.128 mole, the given quantity, be reacted with the lead nitrate. The remaining, the difference will remain the solution, can never have the reactant to react with. Right? So, in other words, this will be the lead nitrate will be the determining reactants. Soon after it's completely gone, the reaction will be stopped. There's no more reaction can go on because one of the reactants is gone, right? How do you understand this? We're going to give you an analogy, but now we try to understand. So this one will be considered as we call limiting reagent. Why? The amount, the number of moles of this one will limit the reaction, go beyond this amount can be reacted. In other words, this amount of lead nitrate completely consumed, no more reaction can go on, right? So in the analogy is, if there's a battered wife, right, and then had enough, right, told the abusive husband, now that's it, I'm leaving you, and then you want to cuss, you want to beat, you beat the wall, cuss the house, I'm leaving you, I'm not coming back. So the wife, the battered wife is the limiting reagent. If the wife's gone, the abusive husband try to beat her no more, right? Because she's no longer in the house, right? So that's the the end of the argument, end of the abusive relationship, that's what we call limiting reagent. The abusive husband has nothing to react with the wife he used to beat, right? Now the wife is gone, right? So in the same case, here the limiting reagent is complete, consumed means it's gone. No more reaction can go further beyond that point because it doesn't matter how much of the sodium sulfide still left inside solution. There's no more lead nitrate to react with. Is that clear? So we understand that. So now what we need to put here, right? The amount of the lead nitrate is going to be the limiting reagent. So the limiting reagent is going to be this one, right? This one, the limiting reagent, right? The limiting reagent. Now, so if this limiting reagent, this is amount is going to be left over. So we have to work. Since we find the limiting reagent, that will become the criterion when the reaction will stop. So the mole ratio between the reactants and the products from the balancing reaction equation, it doesn't really fit into this relationship right here, the quantity. So we have to reset to find new mole ratio based on what? Based on the limiting reagent. If the limiting reagent is considered as 1 here, and then what is going to be the 1 for sodium sulfide? Of course, in this case, it's quite simple. It's a 1-to-1 ratio. So if that's the case, then 1-1-2-1 is going to be 0.03, 0.03, 0.06, 0.03. Is that right? It's still 1-1-2-1 ratio. Is that clear? So that's simple. So let's see. The reset mole ratio. Based on what? Based upon the limiting reagent, right? So what is that? That is going to be 0.03. Here is going to be 0.03 as well. So 0.03 mole will be reacted with 0.03. Now let's just forget about O2. Let's simplify it, right? Then what we have is going to be, that's how much the reactants will be consumed. Alright? Alright? And then that is how many moles of the products can be produced. Twice of this. So here, the sodium nitrate would be twice of 0.03 would be 0.06 mole. Right? Now how many PBS? Lead sulfide, of course, still 1-to-1 ratio, so it's going to be 0.03 mole. Is that clear? Right? Now, then if I keep on asking, well, if this much of the sodium sulfide will be reacted, and you say it's not going to be completely consumed because more than that is given, right? So you definitely have a little bit left over, right? How much left over, right? So we are able to put here, so another item, so the number of moles of unreacted, right? Unreacted, right? Unreacted what? So you do what? You do subtraction. Now it's going to be what? It's going to be 0, it's going to be 8, right? And then 9, right? And 0, 0. So 0.098 moles, almost like a 0.1 moles, right? will be what? Left over. Unreacted. Left over unreacted. Right? And how many moles of the lead nitrate will be left over? Nothing. Because why? If you subtract here, and then 0. Right? 0 mole will be left over. Correct? And of course, this is how many. Now, if we ask you, now this is going to be a aqueous, this is going to be solid. How many gram of PBS, lead sulfide, can we get after the reaction is finished, right? So what are we going to do? We're going to have to find out the gram formula weight. Now here is almost out of space. So let's say if we asking for, it's not a little bit, 13, right? Right? How much precipitate? How much precipitate can we get, right? Can we get? Right? So we have 0.03, right? 0.03 mole. So what we do is I use this space. So the gram formula weight, let's say, so gram formula weight for what? For PBS, right? PBS, Public Broadcasting System, right? Is that right? Public Broadcasting System, PBS channel, right? Is equal what? Equal, let's see, PB 207, right? 207.2, and sulfur is 32, right? That gives us what? Give us 239.2 gram per mole, right? Per mole, right? So, do we have 1 mole? No, we don't have. How many mole we have? We have 0.03. So this one multiply 0.03, right? Right? That would be what? So, yes, okay, 239.2 times 0.03. It will be 7.176. So we'll get 7.17, huh? Yeah, 176. 6 gram of PBS. Alright. So in the homework, alright, as well as the upcoming final, this is not stopped here yet. And the next few items, 14, 15, 16 will be, would you please write the complete chemical reaction equation into the complete ionic equation. Now let's do this. So let's keep it here. Let's see which one is gonna be. Let's start here. Okay. So if you already taken down the notes, right? We still have to have space to write something. We're still not finished. So here we finish the calculation. Alright, so number 14 is right here. Alright, number 14, let me take this out because it's gonna be too crowded. Alright, now let's leave this out too, the mole ratio. Since we finished the calculation, the mole ratio no longer need kept on it. So 14, right? Complete ionic equation. Now when we write complete ion equation, what we have to pay attention is, whenever we run into a compound, it's ionic, it's soluble, right? In the aqueous solution, they are supposed to be ionized or dissolved, dissociate, and ionized into cation and anion pairs. So in this case, this is soluble, so we have sodium and the sulfide will be separated into cation and anion, but we have two sodium. So the two subscript, no longer under the subscript, we're going to be put down there in front as coefficient, because these two sodium atom in the molecule is in subscript. But when you dissociate ionize into iron, they become two individual sodium 1 plus cation. So here we have to pay attention. Now that is all has to be learned, and in the more detailed way. Now not just rush. Now that is I don't care if you're good in chemistry a long time ago, you've forgotten, right? But here we need detail. We need to slow down, right? We need to learn something. And then the sulfide separate from the sodium, it become a anion in the solution. So you have sulfide and 2 minus, and also aqueous. So this compound becomes these two iron pair, right? And then the lead nitrate, you got 1 lead and lead nitrate 2 plus and cation, right? Inside the molecule, inside the compound is a plus 2. Outside ionized become 2 plus. That's a charge, that's oxidation state. Inside here is plus 2 right here, plus 2. Now used to be, right? Here's plus 1 and it's minus 2 for sulfur, right? Then you have to add the nitrate. How many? 2 of them. Each one is 1. So you got 2 in the compound formula. When you dissociate and ionize, become what? 2 anions. Not ionize, not anions. Parenthesis 2 outside. No, it's not. It's going to be 2 nitrate, right? 1 minus and the aqueous, right? And then these two are these two pairs of cation and anion. These two cation and anion pairs, right? Come from what? Come from the reactants. Products. This one, sodium nitrate, is 100% dissociated into cation and ionized pair, right? So you have, this time you have 2 sodium and aqueous and 1 plus. And also you have 2 nitrate, but this 2 is coefficient in front, taking care of the whole thing behind, right? So you have 2 nitrate, also aqueous, and it's 1 minus. Then you have the PBS. What are we going to do with PBS? It is insoluble. Insoluble means what? Insoluble means it has very, very little, 10 to the minus 12, 10 to the minus 15 maybe 10 to the minus 18 moles, very little, will dissociate and then ionize into lead 2 plus and the sulfide 2 minus cation and iron pairs. But soon as that little quantity is in the solution, then that solution considered already saturated with the Pb and S, Pb 2 plus S2 minus cation and ion pairs. No more, alright, PBS can be further ionized. Or you have to say this, let's put this way, it's supposed to say this. Well, we did not get that far yet. We'll just give you the idea. It's a dynamic, it reaches a dynamic equilibrium. So you have a 1 or 2 PBS dissociated ionized into Pb 2 plus S2 minus. The same time, there's 2 or more, 1 or 2 lead, right? 2 plus combined with S2 minus become PBS back to solid again. So the dissociation, right, and the reassociate again become iron compound. That's kind of dynamic equilibrium is established and is going on forever. But only reach a certain very, very low concentration, 10 to minus 10, 10 to minus 15, 10 to minus 18, I don't know exactly, but you can check the handbook, they give you the data. And then you know majority, large majority, 99.9999, 99999% stay as PBS, a solid insoluble compound, right? So this is going to be considered as insoluble as solid, not going down, still there, right? So that is a complete ionic equation. Now, then we have another task to find spectator, right? Spectator. It may have spectators, right? Not just one, maybe two or three. Most of them are two, not three, all right? Spectator. Now we check. 2 sodium 1 plus aqueous on this side as reactants. Do we have 2 sodium 1 plus aqueous on the other side? Yes, we have 2. Everything same. So this is the first spectator. We are able to cancel that, right? Cancel that. And so we can put down here. Now put them here carefully. You have to put the coefficient, right? Right? Exactly in the equation, in our equation, right? That's the first one. Do we see another one? Sulfide? No, that sulfide is connected with the lead, right? So it's not. Lead is connected with the sulfide. So that too is going to be connected to the insoluble product. But this one nitrate. Do we have nitrate? Yes, we have 2 nitrate, 1 minus aqueous solution, aqueous, and the 2 nitrate. So this one is identical with this one. They are able to cancel that, right? So we have 2 nitrate and 1 minus, and also aqueous. These two are the spectators, right? After we find the spectator, now the next step is write a net ionic equation. In other words, we rewrite the equation without a spectator. If the spectators are already cancelled because they're identical. We treat chemical reaction equation just like a mathematic equation. The same term, right? There's a law in mathematics. There's a law. Add the same term on both sides of the equation is still valid, or subtract the same term on both sides of the equation is still valid. The same thing here. We subtract same term, identical on both sides, the equation is still valid. So the net ion equation is the ion equation without what? Without spectators. So what is that? This and that. We may just switch because this is the matter that goes first on the left. So you have this. So you have a PB, right? 2 plus aqueous, right? And react with sulfide, 2 minus aqueous, gives a one-way reaction, give a PBS. And that is solid. Now this is what? This is a net ion equation. Let's check 2 laws of conservation. 2 conservation laws. Are they all satisfied? For the mass, the law of conservation of mass. 1 lead, 1 sulfur, 1 sulfur. So this equation satisfies the law of conservation of mass. Then the law of conservation of energy. The energy use the charge to represent energy in chemical reaction writing with ionic species present. On the left, the lead is 2 plus, the sulfide 2 minus. They combine into give it a 0. And on the right, PBS is a neutral compound, insoluble, of course, is 0. So the law of conservation of energy is satisfied. So this equation fit into, right, law of conservation of mass, right? Law of conservation. Oops, sorry. Conservation of energy. Both check. They satisfy. Right? Now, in this particular case, we don't have, but if we want to, is the second guess, is this redox? The answer is no, because why? Check the complete ionic equation, right? And everything, they have the same oxidation state. Before and after, or you call charge, it's called oxidation state, actually considered as effective charge inside the compound, right? They didn't change. 2 minus 4 sulfur, here 2 minus 4 sulfide, right? Sulfide. And then 1 plus and 2 plus for lead, 2 plus for lead. So there's no electron exchange, no electron transfer, not redox. Not redox, right? Now in this case, we have something left off. 0.098 moles of what? Sodium sulfide, right? And the sodium sulfide left off, we are able to recover it by what? By evaporating all the water solvent, right? This aqueous solution become evaporating all the solvent, and the leftover is we suppose to have this is a PBS solid, right? Precipitated out of solution down to the bottom of the beaker, and then we use a funnel and the filtration paper, right? And then we pour the solution, mix them and over the filter, and then the solid PBS will remain on top of the filter, right? And then we can get it afterwards, and then we dry it and steam dry it, and then we can get PBS solidness compound. And the remaining solution still have what? Still have almost 0.1 almost 0.1 mole of sodium sulfide. And how can we get it? I just said evaporating all the water, put on the drying dish, right, and over the boiling water, and then keep on boiling the solvent, water solvent off, and finally we'll have a crystal sodium sulfide and remain on the bottom of the dish, and you can get it. That's how you recover it, right? But for something, we already had one problem I gave you in the homework. I don't know if you did or not, but if you did not, you should look at the solution on the handout called Stoichiometry. It is a reaction involve a compound and then with a base, and then if the reactants does not have exactly the mole ratio presented on the balanced chemical reaction equation, and one of the reactants will be left over some quantity, then I did not ask you how much that will be left off. I want you to put in litmus paper into the remaining solution, see what color you can get. If it's purple, that's neutral, because the purple color for the litmus paper is purple. If it turn blue, that's going to be basic alkaline, and the basic solution which has a base in there as leftover compound as a reactant. If it's not, it could be red, it could be acidic. Now that's only happens when you have acid and involved. If it's not acid involved, then it's not going to be turned red. But if you only have exactly same mole ratio, we call it equivalency, and then the whole solution left over is going to be completely neutral, and the litmus paper will remain purple. Now that is another story. We already time's up, and I think I already have enough and don't have enough time to continue for more, so I will have to say we finish the course.